So the goal now is to transition to continuous space. We've made the transition from discrete time to continuous time. Now we'd like to move over to a state space that's continuous, namely a state space that's equal to the real numbers. So picking up from before, this is our time interpolated random walk. And so hopefully you know how it works. This part related to the original discrete time random walk, which is right here, just the sum over k increments. And we've discretized time. We've taken little time intervals delta t and a continuous time index t, and just connected all the positions of this random walk by lines. And now we're going to do the same thing with space. So let delta x be the displacement of a particle in time delta t. So again, going back to the video, every single time that this blue particle gets hit, that happens in a small interval of time delta t, during which it gets displaced by some amount, and that amount is going to be our delta x. So what we arrive at very quickly is, from the interpolated random walk. So again, starting from a random walk, we get the time interpolated random walk, and we now arrive at the scaled interpolated random walk, where all I've done is taken s of t and multiplied it by the displacement. So why is this the case? If you just look back here or up above, every single one of these increments is either +1 or -1. And if I multiply from the left by a small amount delta x, then what's going to happen is that my increment, the amount by which I've moved, either in this case in one dimension to the left or to the right, or in 3 dimensions, it's going to be up, down, left, right, forward, back. I've reduced the size of this increment from 1 to delta x, to whatever I want it to be. And the goal is that we'll start taking the delta x and delta t down to 0, which is essentially, if you want to think about what's happening in the context of this video here, what we're really doing is we're modeling the fact that this medium that the blue particle is suspended into is made up of many, many, many other particles. And the more of them there are, the faster, the smaller the time interval delta t that it has. So it's getting hit, the blue particle is getting hit more and more frequently, and the time between each displacement becomes smaller and smaller and smaller. You could just think about sort of pouring more and more particles into this container, and so you'll all of a sudden see things kind of accelerate. There are more particles that will hit the blue one, and the displacement will also be smaller. There will be a small interval of time during which it will move before it gets hit again from the other side, and so on and so forth. And so the picture you want to have in mind is this scaled interpolated random walk, which I'm writing it as W delta. So delta is going to be kind of how many is, in some sense, delta is some very small number, which corresponds to as delta is, for small delta, we're thinking of more particles in this box here. So the more particles that I pour into this liquid, the more dense I make this material, the smaller my delta is. And so W delta is going to be a scaled interpolated random walk. And if you just set delta x equal to 1 and delta t equal to 1, you will recover this guy right here, the interpolated random walk, and it looks kind of like this, similar picture to the previous clip. If I make him a bit smaller, it starts looking something like so. And then if I make it even smaller, I'll get to something that looks like this. And you keep doing this over and over and over until you eventually get to the kind of drawing that I had on the very first overview video. And one thing to keep in mind is that as long as these are finite, as long as they haven't gone to 0 yet, driving all of these pictures, which are kind of representations or approximations for the Brownian motion, is still the original random walk. So we really haven't done much of anything. The underlying process that's driving this is the discrete time Markov chain, the discrete time random walk on the integers. But as we scale it in time and in space to make sort of small increments between it moves and displaces, we start seeing this this process approximate the Brownian motion, or what we're going to call the Brownian motion, closer and closer and closer. So it's a better and better approximation to what we're going to call the Brownian motion as delta x and delta t tend to 0. But for any finite delta x and delta t, we can always still convert back to discrete time and discrete space. So we can always come back to here. This is a Markov chain for which time is discrete, it's a natural number, and for which space is discrete. The values that this takes, the state space of this Markov chain is the integers, and here I recover both for you. Given a continuous time index t and a displacement time delta t, if you divide them and take the integer part, I'm going to claim that's my k. The number of time steps, that's also equal to the number of bombardments, the number of times the blue particle has gotten hit by time index, by continuous time t. And here is going to be my position in space. So if I take x and divide it by delta x, that's how far I am from the origin. If I started at 0, which is what it's going to be kind of a canonical choice for us, we're going to always start at 0 unless told otherwise, which is why I've drawn each of these paths starting at at 0. If you take delta x, which is the position somewhere along this axis, and divide it by delta x, the number of displacement, that's you get a position, or the integer that sk is equal to. So at time sk, the value of this random walk is n, which is equal to just x divided into how much I move at every single time. I've moved a total distance of x from the origin. I've moved by an amount, a displacement amount delta x each time. So if I divide the two, I get the position in the integer state space, which is where this process lives. So now we're kind of ready to start looking at what actually happens when you take delta x and delta t down to 0.